Hi everyone, welcome back to my semester design project for Engineering 1315, where we're talking about a double pulley system. So in the last couple of videos, we went through and found the effort force mathematically and experimentally for 3 different objects. So today I'm going to discuss the results with you and what we can really take from all that. So first we got to talk about our constants. So first we have U, which is equal to the mechanical efficiency. Now for the sake of this diagram, I assumed everything was frictionless, just to make it easier, and so that would have the mechanical efficiency at 1. And N, which is equal to the number of wheels, would be 2, because it's a double system pulley. Now if we go down to our equation, that shows you that throughout the entire thing, our denominator remained constant, because we always had a mechanical efficiency of 1, and we always had 2 wheels for each 3 of the trials. So our other factors are effort force, which is what we're looking for, mass, which is what we changed, and G. I didn't actually talk about this before, but the distance I yanked each of the pulleys down was about 1 foot. I didn't mention it because I forgot to put it on my talking card, but anyway, that's important because grams is measured in meters per second squared. So the more distance, the bigger the number. So we wanted to keep that as constant as possible as well. So I only yanked it down about 1 foot. So the only changing variables now are effort force and mass. So we can really see the relationship between these two because we kept everything else constant. So let's look at our numbers. So we have our water bottles, which were about 1 kilogram, and we got a little over 5 newtons, where when we go over here, this shampoo bottle was about 1/2 kilogram, and we got almost half what we got here. I find that very interesting, and this number actually falls somewhere in the middle of that proportion there. To demonstrate this, I did make a chart just so it would be easier to view results. It's still a rough estimate, but I think it drives the point home well. So I took our 3 points. This would be the water bottles, this is the candle, and this is the shampoo bottle. And I just graphed them. So we got our force on the Y, we got our mass on the X. The mass is what we controlled, kinda. It was the effort force dependent on the mass, so that's why these are where they are. But yeah, it shows a positive line of best fit. In order to figure out what the equation for that was, I used the linear regression equation, which is something we discussed in lecture for Engineering 1315, but because it's kind of irrelevant for the sake of this video, we're really talking about pulleys and efficiency, I just did the math myself. So same thing I mentioned before, it shows that you get a positive slope. So as your mass increases, the force increases, which makes sense because, you know, a pulley might help make things easier for us in life as it is a simple machine, but it doesn't take away all that's required. So if you have more mass, it makes sense that you still need to put more effort. And another thing I wanted to talk about was this number right here. So we talked about the slope, how it was a positive number, and how that made sense. So this number, the 0.0038, I think that just shows that our graph is pretty accurate, because this number should be 0. When you think about it, if you have no mass, it shouldn't take any effort, right? So this should actually go straight through the origin. So this indicates that it was a decently accurate estimate, which is great. So yeah, I guess that's really all I have to say for the results. You can really see how mass and effort force are connected.